So let's take on a few sample problems here. Our first sample problem, we have a standing wave with a frequency of 30 hertz, and it's generated on a string that is 10 centimeters long, and it's fixed at both ends. We see that one antinode is observed, and we're looking to find the wave speed. So let's sketch it. Here's our string. We know that one antinode is observed, and since it is a fixed at both ends, we have nodes on both sides. Therefore, what we have is our fundamental or our first harmonic, and that means we have 1/2 of our wavelength, because from node to node is 1/2 lambda. The other information we know that the length here is 10 centimeters. So based on this information, we can solve the problem. So given, we know that the length is 10 centimeters, which is equal to 0.1000 meters. We know that we're on the first harmonic, and we are looking for the speed of the wave. Well, in this particular case, we know that wave speed is equal to f times lambda. Also forgot that we do have the frequency, which is 30.0 hertz. That's pretty important too. In our particular question, we know that it is the first harmonic fixed both ends. So the other thing we know is that the length of the string, L, is also equal to 1/2 of our wavelength. So V equals F lambda. But L is equal to 1/2 lambda, or 2L is equal to lambda. So we'll sub 2 into 1, and we get V is equal to F times 2 times the length. So 30 hertz times 2 times 0.1, we get a wave speed of 6.00 meters per second. All right, let's take a look at example number 2. A piece of PVC pipe can often be used as a speaker port in a homemade subwoofer box. What is the minimum length of pipe? What minimum length of pipe is required in order to have a system resonate at 50 hertz? All right, so we know what our frequency is. We know our frequency wants to be 50 hertz. We actually have the speed of sound. It's given as 340. So we're looking for the minimum length of pipe in order to cause the system to resonate. So specifically, we're looking at PVC pipe. All right, so we're going to go with the concept first. What I'm going to do here is I'm going to represent a piece of PVC pipe as follows. Now, there are two configurations we can have. So this is our pipe, and right now, this pipe is open at both ends. Now, beside it, or should I say below it, I'm going to have the same configuration, except now what I'm going to do is I'm going to do fixed at one end. So I'm going to close up one end, and I'm going to represent that by putting a line there. So with the PVC pipe, technically there's three versions. I could close it at both ends, but that wouldn't make any sense here. So let's take a look. So first of all, we have to decide which configuration, because we want the minimum length. Now, here's the thing. The lower the frequency, the longer the wavelength. So lower frequency, longer wavelength. Higher frequency, shorter wavelength. So in other words, we want to get the biggest wave in there. So which configuration makes the most amount of sense? Well, we know that the length of the pipe is represented by this. So we want to see which of the two configurations works best. Open both ends, close both ends. Well, if it's open both ends, here's what I know. I know I have to have an antinode here, and I know I have to have an antinode here, and in the middle, I'm going to have a node. So it's going to look something like that. Whereas in fixed one end, I'm forced to have a node here, and I'm forced to have an antinode here. Surprisingly difficult to draw this. So if we take a look in this particular case, I know that the distance between antinode and node is equal to a quarter wavelength. So that's another quarter wavelength. So in this case, the length of the pipe is equal to 1/2 lambda. But in this case, this length represents just a quarter lambda. Well, if you take a look, if we were to take a look at both of these waves, and just to give you some context, this here only represents 1/4 of the wave. So the full wave would be 4 times longer than this length. So the full wave would be 4 times these lengths. Well, in this case, the full wave is only twice as long. So that means this frequency is going to be higher because this wavelength, physical wavelength, is shorter. A quarter is only this amount, but in this case, a quarter is the full length here. This represents a much lower frequency wave because the wavelength is so much longer. The whole length of this pipe represents a quarter of the wave. So if, let's say, for example, this length is 10 centimeters, then the wavelength would be 40 centimeters in this case. And in this case up here, the wavelength would be 20 centimeters. So this would be double the frequency. So which one naturally produces a lower tone is this configuration here. So in this particular configuration, produces the lowest tone, which means we require the least amount of material because we want the minimum length of pipe, which means we want the lowest frequency possible. Well, to get the lowest frequency possible requires us to have a fixed one end resonating system. And this requires least amount of material because the length of pipe that we have here only needs to be equivalent to 1/4 of the wave. Whereas in this configuration, we would need double the amount of material to resonate at the same frequency. So this is the configuration we want. This is a waste of money. All right, so let's solve it. So here's what we got. We know that our frequency is equal to 50 hertz. We know our wave speed is equal to 340.0 meters per second. And we have determined that we're going to use the first harmonic fixed one end. And we're looking for the length of pipe. So the formulas are as follows. V is equal to F lambda and L is equal to 1/4 of our lambda. Let's draw our diagram. So here's our pipe and our wave open at both ends. That's our length, node, antinode, and our wave looks something like that. So our length is 1/4 of our wavelength. So in order to solve for the length, we need to find lambda. So let's find lambda. V equals F lambda. Isolating for lambda, V over F is equal to lambda, or lambda is equal to V over F. Substituting in, our speed is 340. Our frequency is 50. 6.8 meters is our wavelength. So now we can find our length. Length is equal to 1/4 lambda, which is equal to 1/4 of 6.8. For a grand total of 1.7 meters is the length of pipe that would be required to resonate at 50 hertz. 1.7 meters is a fairly long length, but what you can do is no one said that the pipe has to be in a straight line. And in fact, that's how a lot of modern speakers get away with doing this in a shorter physical space, as they basically fold the resonating air column in on itself, which takes up significantly less length. So you can fold up 1.7 meters into something more compact. All right, let's take a look at example number 3. It says, what would be the next two resonant frequencies of the system in question 3? All right, so let's take a look at what that means. So now in the last question, and that should say actually question 2. Let's fix that. So in question number 2, it said, what would be the next two resonant frequencies? So let's borrow some information from 2. Let's get the length and the configuration. All right, so this was the first harmonic. All right, so let's take a look at what the second harmonic would look like. Sorry, not the second harmonic, the next harmonic. So now we have to change the configuration a bit. So we've got to get rid of our wave here, and let's get rid of this. So the next thing is, I know that it's got to be a node and antinode, but in order to complete this, the next mode of resonance, instead of having just one na, we have to have two nas. So we have to have an antinode and a node. And we got to make sure that these things are spaced out evenly. So the distance between node, antinode, node, and antinode are equal. So in this configuration, this is equal to, from node to node, 1/4, 2/4, 3/4. So in this case, the length is equal to 3/4 lambda. And this is our third harmonic. All right. So let's figure out what that frequency is going to be. Well, we know from the previous question that the length was 1.7 meters. So in order to find that frequency, I know that B is equal to F times lambda. So my frequency is going to be equal to V over lambda. All right. So we have to do a little aside to find our lambda. So our lambda is going to be based on this. So isolating, we're going to get 4 times L over 3 is equal to our lambda. So lambda is equal to 4 times 1.7 divided by 3. And that gives us 2.26 repeated meters. So when we substitute that in, we got F is equal to 340 divided by 2.26 repeated. And that works out to 150 hertz. Now, if you notice, the third harmonic is 3 times higher than the first harmonic. And this frequency was 50 hertz. So 3 times 50 is 150. And then we repeat. So again, let's take a look at the next mode. So in the next one, instead of having 2 NAS, now we have to have 3 NAS. 1, 2, 3. So let's make sure that we get them spaced apart nicely. Draw in our wave. And then we count the quarters. So that's going to be 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters. So in this case, L is equal to 5 quarter lambda. And we basically can repeat the math. So now we get a wavelength of 1.36. Substituting in 3/4 divided by 1.36 and 250 hertz, which is 5 times bigger than 50. And for question 4, let's try that one for homework, and I will post the solution for this one in the following days.